All right, so here we are to talk about therapeutic ultrasound. So let's go ahead and get started here. Objectives, you can read through these, but you need to know the basic science. You need to be able to apply it and establish a plan of care for your patients and do that within the appropriate parameters for the application for this modality. Okay, so we're going to talk about the physics and some terminology, lots of terms here to learn. Look a little bit at application techniques. Going to cover that a little bit more in lab, and various indications, where we're going to be using ultrasound in the clinic. Okay, so where did ultrasound come about from? Well, the first large-scale application actually came in approximately World War II with the invention of sonar. So they were building these sonar systems and learning how they could detect things underwater and navigate submarines. And they found that with the strength that they were using of the sonar, that they were killing fish. And not only were the fish killed, but they were heated. And so the high-intensity ultrasound was killing the fish. And so that led some smart individual to think, wow, if we can heat tissue, maybe we can do something else with that. And so that led to research in tissue heating, and ultimately what we see today with tissue heating and some of the healing effects that we might possibly see as well. So the number one thing to get from this right away is it's found to preferentially heat tissue with high collagen content. Right. So as we go along, just keep that in mind when we're trying to heat things, is that if it has high collagen, ultrasound does work well for it. If it doesn't heat it very well. So keep that in mind. Okay, so what is ultrasound? Okay, so ultra meaning high or high frequency. It's just high frequency sound, and by definition it's sound that has a frequency of greater than 20,000 hertz, and it's transmitting this sound by compressing and rarefying, or kind of making wider or bigger a material. In this case we're using a crystal. And therapeutic ultrasound is defined in the United States is from about 0.7 to about 3.3 megahertz. Our units are usually at 1 and 3 megahertz. Some of our units in the lab do have a setting for 2 megahertz. But primarily what you're going to see are 1 megahertz units and 3 megahertz units. All right, so a few of the properties then of ultrasound is, keep in mind that as it moves through whatever medium it's going through, that's going to attenuate or decrease, as it's shown in the graphs right here. So it's going to be strongest right where it's leaving the face, and then decreases depending on what is between on what it's passing through. Okay, and we have two physical effects that we're going to try to take advantage of. One of those is thermal, and this just comes about from the vibration of the molecules, and that tends to increase heat. And then we also have non-thermal effects, and those non-thermal effects are termed acoustic streaming, cavitation, and microstreaming. And there are many proposed effects of these non-thermal effects. One of them is to alter cell membrane permeability. This is the effects that we're going to try and maximize when we're trying to use ultrasound for wound healing, so other than heating things up. So how does this thing work? How does this device work? Well, some materials have a property that's called the piezoelectric effect. And what that is when we deform that material, it produces a small bit of electricity, as shown in the diagram here. Now, one of the things that we can do is we can reverse that, and if we put some electricity into a material that has the piezo type properties, you get a mechanical deformation, and so it actually starts to vibrate. And so what we're doing is we're taking a special crystal, we're putting electricity into it, and it vibrates. That head vibrating then responds by giving us the ultrasound, or the high frequency sound waves that come out of our ultrasound wands. So a little equation down here, it says the optimum frequency for ultrasound is C divided by 2 times T, where T is the thickness of the material of the crystal, and C is the speed of sound in the material. So not that you need to memorize this equation, but the thing to keep in mind is that you see the thickness. When we change our settings on our machines, we don't have a thickness setting. We don't have a the ability to change our crystals, so it's set at one thickness. And so if this equation gives us the optimum frequency, then we have a problem here because we're switching all the time on our machines from 1 to 3, and like I said, some machines have 2 megahertz. And so the manufacturers have made some compromises here in order to produce an ultrasound machine that can perform at more than one setting. All right, so I've already alluded to 2 ways that we'll typically use ultrasound, and that's in a continuous mode and in a pulsed mode. In a continuous mode, as shown in the diagram right here, this looks awfully like our direct current, and so when it's on, so it's running continuously. This is the one that's going to generate heat, and we're going to use it to heat things up. Our pulsed ultrasound is going to produce little or no heat, and that's going to be dependent on the duty cycle or how much time it's on. As you can see, as my duty cycle goes to 100%, it approaches continuous ultrasound. So when it gets higher and higher, the duty cycle, when it gets higher and higher, it is going to produce heat. So pulsed ultrasound, though, is typically only used at 20%. So just keep that in mind. All right, so we typically use 2 different frequencies, 1 and 3, and that frequency is just the number of compression refraction cycles per unit time. And so the thing to keep in mind with choosing a frequency is you're going to look at depth of penetration. So the higher the frequency, the lower the depth of penetration. Okay, so as it says here in the second bullet, increased frequency, decrease in depth of penetration. And that's shown in both the diagrams that you see to the right, just showing the depth of tissue by 1 megahertz, which is deeper, usually about 5 centimeters or 2 inches or so. And then 3 megahertz is usually 1 to 2 centimeters, so a little less than an inch. Okay, the other one that shows the curves there, temperature and depth of tissue, also shows you that while we get deeper heating out of the 1 megahertz, we also get more rigorous heating out of the 3 megahertz. Okay, so it's shallower and hotter, and the 1 megahertz is deeper and not quite as hot. So just keep that in mind because that's going to make a difference on how you set your treatments up. So we talked about the duty cycle when we talked about E-stim, and that's just the portion of total time that the ultrasound is on to the total cycle time. All right, so some examples are given right here in that if the ultrasound is on for 5 seconds and off for 5 seconds, so that's just 5 over the total time for that cycle, which is 10, we get 50%. So that would be an example of a 50% duty cycle. So if it was on for 2 seconds and then it cycled on a 10-second cycle time, so it was off for 8, on for 2, then you get that 2 on over 10 total. That's 20%. And again, that's typically what you're going to be using in the clinic, is that 20% duty cycle when you're using pulsed. So power, lots of stuff here. All right, so power is defined as energy per unit time, and that's given in watts. All right, so the intensity, or what we're dialing into our machines, is usually given to us in that power per unit area, or watts per square centimeter. So as you're turning up the intensity, that's what you're typically reading off of the screen. Okay, so we can look at that intensity, though, in 2 different ways. And 2 different ways that they are defined as the spatial average temporal peak, or the SATP, and the spatial average temporal average, or the SATA. So the SATP is what we are reading off of our meters in most cases. So as you're turning that up, that's the spatial average temporal peak. And that's the spatial average, which is just the average intensity over the unit area during the on time of the pulse. All right, so it's an average over the on time. And so the spatial average temporal average, or SATA, is the average over the on and off. And so the reason for these 2 different types of readings like this, part of it depends on the literature that you're reading. In most of our literature, we're going to be mainly looking at the SATP, and in most non-scientific, a lot of times they'll be reporting the SATA. And so, well, why is that important? So if you look at the diagram, you can see that the SATP we set that at 1 watt per square centimeter, and we're running it at a 20% duty cycle, okay, then that's equal to an SATA of 0.2 watts per square centimeter. So if you were trying to get a similar treatment effect, you really need to know how something is being reported. And you should be seeing that in most of our literature now. It should be reported as to what they used, SATA or SATP. All right, so just know that at 100% duty cycle that the two are equal. All right, so one's just going to take into account the duty cycles it shows here in the little equation. SATP times the duty cycle is equal to the SATA intensity. All right, so we can talk a little bit about a thing called a beam non-uniformity ratio, or BNR, and that's a ratio of the spatial peak to the spatial average. All right, so if you look at this diagram, and you know, it looks kind of like a bunch of mountain peaks, or even like the fingers of your hand. You know, you've got a long finger and you've got shorter fingers, and so the ultrasound beam, as it comes out of the head of the transducer, is not symmetric. And so what the BNR ratio here is giving us is some idea of how symmetric that beam is. Okay. With a BNR of 5 to 1, and if we've turned that up to 1 watt per square centimeter, our peak intensity is given to us as 5. All right. So what we're doing is we're taking that peak intensity, so the BNR is 5 to 1. It's showing what our highest peak could possibly be. All right, so if we look at what our machine is putting out, then if we take 5 times that 1 watt per square centimeter, just reading that off of our meter, well, we have a peak out there somewhere in our beam that's 5 watts per square centimeter. And if you've ever done an ultrasound, you have never turned an ultrasound up to that kind of intensity. You're going to burn someone. Well, the take-home point here is that you actually do have peaks like that are being output. All right, but they're small peaks. And so, but if we look across the average, okay, our average, that's why we're talking about this spatial average intensity, is going to be 1. But there are some long fingers out there, or high peaks out there, that are actually as high as 5 watts per square centimeter. And this is one of the major reasons why we need to continually move our ultrasound as we apply this treatment, so we don't end up burning someone with that high part of the beam. Okay, so we could do another little equation like this, or another sample, that if our spatial average intensity is set at 1.5, in other words, that's what we have the machine turned up to, and our BNR is at 6 to 1, which is what the FDA requires it to be, 6 to 1 or less. Okay, our peak is just that 6 times the 1.5, and so that gives us a 9 watt peak. Okay, so again, that's a huge chunk of energy out there. So you can see that the lower the BNR, the better off we are, because it's going to give us a much more uniform beam. And if you have any experience doing ultrasounds, you know that as you move from machine to machine in a clinic, some machines you can move slower and seem to give a better treatment than others, and that's a lot of a factor of this BNR. And if you look at all our machines when we go in the lab, the BNR is listed, but these days all they list is what the FDA requires, is that it is less than 6 to 1. Okay, so that's just the FDA requirement. You don't really know what your BNR is. But the better the crystal, the lower the BNR is going to be, and it's going to give you you're going to have an easier time of giving a treatment to someone, not have to move the sound head quite as fast. All right, so the effective radiating area is just the area of the transducer head that energy radiates from. Okay, and it looks something like this, in that the transducer face usually has a little bit of an area that there is no sound energy coming out of, and that's also usually listed right on the ultrasound wand as well. All right, so I mentioned attenuation when we first started here, and that's that decrease of the ultrasound energy as it passes through material, through our bodies, through our skin. Okay, and that is attenuated. It's a combination of absorption, reflection, and refraction. And So that attenuation is happening because we're converting the mechanical energy from the vibrations into heat energy. And so that's going to be very dependent on the frequency that we've chosen and also the tissue that we're going through. And I mentioned earlier that it's highest for materials that have a high collagen content, and it also increases when we're using that higher frequency as well. So looking through the table right here, we can see that blood attenuates ultrasound very low, 0.12 decibels or dB per centimeter. But if we look down to bone, it's very, very high. Okay, and if we look at tendon, we're at 4.9, at cartilage 5.1. Okay, the thing to really look at here is muscle. Okay, way down there at 1.2. So tendon and cartilage absorb this ultrasound energy, 5 times more than muscle does. Okay, fat is another half again down there, so it's at 0.6. So you can see that ultrasound energy passes readily through fat, passes fairly readily through muscle. Okay, and it starts to get stopped when we look at tendon, cartilage, and especially bone. All right, so again, this tells us a little bit about what type of materials that we want to be applying our ultrasound to in order to get a heating effect, and that's things that have collagen in them. Okay, so if we're going over fat, it also tells us that we're not losing a lot of energy, but it also shows us that we probably should not be using this for trying to heat muscle. Okay, especially not muscle that over a broad area of muscle. So we have those 3 factors that affect attenuation: reflection, refraction, and absorption. So what do those look like? So reflection is just what you would think about, like reflection from a mirror or the surface of a lake, and that's redirection of the beam of energy away from the reflected surface, as you see in the first diagram right here, and being demonstrated down below. The key thing here is that means that there's some energy loss. So whenever we have a wave being impacting a surface, some of that energy is going to be reflected back, okay, and then the rest of it's going to go through the surface. And so ultrasound is reflected at our tissue interfaces, and anywhere that there's a change in interface from tissue, bone, air, skin, you're going to have different reflection rates. As you can see there, if we have air, we get 100% reflected transmission. So that's one of the reasons why we have to use gel. All right, so refraction then is, this is like when you take a stick and you're down at the lake and you put it in and it looks like the stick bends. Okay, that's refraction. And so that's redirection of a wave at an interface. And again, the important thing to keep in mind is that we have refraction taking place through any tissue interfaces that we have, and that results in an energy loss as well. And then the third one is absorption. So just like we looked at attenuation, we can look at specific absorption coefficient for different muscles. And this is going to directly correlate with the other table in that blood is very low, bone is very high, tendon and cartilage are towards the high end, but muscle, again, is extremely low. Okay, so again, highest for tissues with a high collagen content, and those are the ones that are going to absorb the energy the most.